Well, thanks for having me here. I'm happy to be here today to talk to you about boosting power efficiency of HPC applications with GOPM. GOPM stands for the Global Extensible Open Power Manager, and it is a new runtime that we've been developing for the past 6 years for power management and power optimization, which promises to significantly improve both the performance and power efficiency of future HPC systems. As the name suggests, it's open source, highly extensible, and of particular relevance to the ALCF community because we're working with Argonne to make GOPM available on IOTA, Theta, and future systems at Argonne. So here's the outline for the talk. I'm going to begin by talking about some of the challenges that initially motivated us to develop GOPM and the approach that we're taking in GOPM to solve those challenges. And then I'll describe the architecture of GOPM, some use cases that we imagine GOPM being used for, some deployments that we're working on for GOPM this year and next and beyond on production systems, and then I'll share some results from our experimental evaluations of GOPM to quantify the performance and energy benefits that it can bring. If there's time, I'll talk next about some work that we have in progress and are doing in the future. And then I'll close with some takeaways and a call to action to join the growing community of GOPM users and developers. So challenges. Our original motivator for GOPM was Exoscale, trying to improve the power efficiency of exascale systems. I say our original motivator was that because the scope has grown since then to include not only future exascale systems, but current systems. We quickly realized as we were developing GOPM that we could make the implementation general, make the optimizations that it does general, so that they'd benefit not just future exascale systems, but also current ones. I think most people are familiar with exascale and the targets that the US DOE has set in the United States for exascale. We want to achieve 1 exaflops system performance within roughly a 45 megawatt power budget and do that in the 2021 timeframe, which is pretty aggressive. It represents significant performance increases relative to current systems and only modest increases in the amount of power we let the system consume. All of that implies that we need to dramatically improve the energy efficiency of systems if we're going to reach those targets. So if you look at the ways that we have traditionally scaled up performance and power of systems, and you estimate the performance and power consumption that we will be able to achieve if we do nothing more than those traditional scaling techniques, unfortunately, we're facing roughly a 2 to 3x gap between what we can deliver and what we'd like to reach for exascale systems. I'm talking about traditional scaling techniques like taking advantage of manufacturing process technology advances and taking advantage of greater transistor density to deliver more performance. I'm talking about things like integrating more and more of the system's hardware components onto the SoC in the same package where communication distances are reduced and therefore you can save energy on data movement. And I'm also talking about fundamental architecture advances, which help to deliver higher performance at a given power level. All of that we expect to play a big role in reaching exascale, but it won't be enough. We're still facing a 2 to 3x gap in efficiency. We also anticipate that there won't be a single silver bullet technology that can completely close this 2 to 3x gap, and that it's going to be necessary to make advances in multiple dimensions. Certainly architecture is a big one. It turns out that power delivery is another space where we're going to need advances. There are a number of inefficiencies in the power delivery system, especially at the 45 megawatt scale that we're talking about. We're going to need advances in software, in the applications and libraries, to enable them to scale up to exascale. And we're going to need advances in power management, which is the focus of today's talk. The focus of the work that we've been doing on GEOPM is really rethinking how power management is done in a system to enable much wiser use of the power that we do have available. We're going to be power constrained in the exascale timeframe. So if you look at the way power management was done historically it was largely the responsibility of the hardware and the firmware to do power management. Software didn't play much of a role, if any. Those techniques wasted a significant amount of power, left a significant amount of potential performance on the table. And that's in large part, owing to the fact that they are more or less node local power management techniques. They make decisions on a per node basis, looking at only the information that's available on a given node. And so they don't have any notion of the fact that applications in the HPC context are massively distributed. They don't understand that there can be load imbalance, there can be a critical path node somewhere remote, and the performance of that node will impact overall application time to solution. So this lack of application awareness is one of the fundamental reasons why historical techniques have left performance on the table. They've also not been aware of application phases and not been able to tailor decisions about what power budget to run at or what voltage and frequency to run at to the unique characteristics of each computational phase. So you can have very distinct computational phases in HPC applications where one may be banging on the compute resources more than the memory and communication resources. Another may be more memory intensive, and yet another may be more communication intensive. And as you can imagine, the right power to run at or the right frequency to run the processor cores at depends on which resources you're banging on the most. For example, if you're in a memory limited or a communication limited phase, it makes no sense to run the processor cores at full bore. They'll end up just generating memory references or communication operations faster than those other subsystems can satisfy the requests. So it's awareness of those sorts of things that's lacking in traditional hardware and firmware-based techniques. And we need to move away from those techniques toward a solution that incorporates some software intelligence about global load imbalance, application phases, and incorporates software layers of power management into the total system power management solution. That software will provide the missing global application awareness and guide the hardware and firmware to better decisions than they can make in isolation. So that's the solution that we've been exploring in the GEOPM project. We've been building a new software runtime for power management and optimization that adds scalable application awareness to power management. This is a community collaborative open source project, like I mentioned. It was started by Intel, but has grown into very much a community project with users and developers at HPC centers around the world. Intel still, of course, supports the project and provides a bunch of engineering resources, but it's a community project at this point. You can find our project page on GitHub. There's a link there to the project page where you can find documentation, source code repository, etc. And what's really neat about GEOPM versus prior power management solutions that have been out there is that it is able to operate globally across all of the compute nodes in a job, analyze the application across all of those compute nodes and look for patterns such as load imbalance or application phases, and then find settings of the control knobs in the system, whether they're in hardware or software, that enable the application to complete faster or enable the application to complete in roughly the same amount of time but at lower energy, whichever you configure GEOPM to do. So the global application awareness of it is what's unique compared to prior approaches. This is very much an online optimization process driven by feedback, application profiling data. We get that application profiling data through some lightweight profiling, which I will talk about in a few slides. Some examples of the kinds of knobs that you can tune with GEOPM include things like the power budget allocated to each compute node in the job, the frequency that the processor or individual processor cores run at, And in the future, we'll be able to tune things like the number of parallel threads that OpenMP parallel regions are running. There's some work we're doing in collaboration with Livermore to add the ladder tuning of OpenMP parallel threads. Some examples of the patterns that GEOPM can detect and take advantage of are, like I mentioned, load imbalance across nodes and computational phases. We've done some experimentation with GEOPM to quantify how much performance or energy efficiency benefit you can get from it. And our data shows that 5 to 30% improvements are possible, which is pretty substantial on its own, but even more substantial when you think about the fact that this was done with software without any special hardware or any changes to the power controls, monitors, features that are available in the hardware. This set of experiments was done on Intel hardware. Your mileage, of course, will vary depending upon what hardware you're running on and what controls and monitors are available. Intel processors have a pretty rich feature set when it comes to controls and monitors. If you don't have a rich feature set, your benefit may look a little lower than that. Mileage also depends on what particular workload you're running. I have a reference here at the bottom of the slide to a paper that we published at ISC last year that goes through these experiments in detail. And later on in my slides, I'm actually going to summarize this too. But before I get there, I wanted to spend a moment describing one of the other fundamental goals that we've had in the project, which is to build GEOPM in a general enough and cross-platform way that would allow it to be a platform for the community to do research on new algorithms and software for optimizing power or energy. Goal being to kind of align the community on a common software framework for this type of research where everybody can share source code and the burden of developing new algorithms and then reap the benefits together as a community as well. To that end, we made GEOPM open source, and it's truly open. We selected a BSD license, which is a very permissive and non-sticky license, so it's suitable for both academic and commercial use and experimentation. We also made it simple to port GEOPM to other architectures, so this isn't locked down to Intel architectures by any means. In fact, there's a port underway already for IBM Power 9 plus NVIDIA. You can extend GEOPM in 2 dimensions presently. We may add more later. The first is that you can extend it to new optimization strategies, and you do that through a type of plugin that we call agent plugins. And the second dimension you can extend it in is porting to new processors where they may have additional control knobs versus the stuff that's currently supported, or even brand new hardware platforms that weren't previously supported. And you do that through a type of plugin in GEOPM that we call I/O groups. I'm going to talk about the architecture of GEOPM use cases and deployments next, but let me pause for a second and see if there are any questions so far. Okay, please interrupt me if you do have any questions. The more interactive this is, the better. So let me say a little bit about the architecture of GEOPM. As I alluded earlier, it is a job level runtime, operates on the job, and tries to coordinate tuning of control knobs globally across all of the compute nodes in a job. For large jobs, if you were to try to do this with a centralized runtime, the problem size would become pretty intractable. And so we don't do that. We don't use a centralized design. Instead, we adopt a more scalable tree hierarchical design and decompose the global tuning problem hierarchically. We literally have a tree hierarchy of controllers in GEOPM, which we map these hierarchical subproblems to. We have GEOPM leaves. There's one leaf running in each compute node. We have GEOPM aggregator controllers. Some of the compute nodes will run one of these as well. And then we have a GEOPM root controller. One of the compute nodes will run a root controller. These controllers all coordinate with each other to orchestrate global optimization, and we do that through recursion and aggregation. Let me give an example, I guess, with power budgeting to make this concrete. The root will try to find an allocation of a job power budget among its children, the aggregators, that, let's say, maximizes performance within that job power budget. Then each aggregator will take the power budget it's been given and do the same thing. Try to find an allocation among its children, GEOPM leaves in this example, that maximizes performance, and so on. At each level of the tree, performance is taken to be the aggregate performance of all of the nodes in the tree below them. So for example, at the aggregator, performance is taken to be the min performance of any of the leaves, and then at the root, performance is taken to be the min performance of any of the aggregators. All of these controllers run extensible optimization algorithms, as I mentioned earlier. You can select what optimization algorithm they're running. We call these algorithms, or these, we call this portion of GEOPM agents, and agents are pluggable, so you can, select which optimization agent you want to run with, and even create new ones. Let me give a little bit more implementation detail, because I know some of you are wondering. How do we access the hardware controls that the hardware provides? We do that through drivers and libraries. For example, on Intel systems, we use a driver called MSR Safe. Controls and monitors for power and performance management are typically exposed through something called MSRs, or model-specific registers. And there's a driver that LLNL developed called MSR Safe, which we use on Intel systems. On other systems, we use similar drivers or libraries. How do we get application profile data? If you remember, this is all online feedback-guided optimization, leveraging application profiling data. We collect that through the instrumentation frameworks that are available in MPI and OpenMP, PMPI and OMPT in particular. And optionally, the programmers can add some lightweight annotation to their application code that tell GEOPM about additional stuff that you can't get from PMPI and OMPT. I'll talk a little bit more about that later. I'll give you an example with one of the plugins and how one of our plugins uses that optional annotation. These controllers all run in the job compute nodes, as I mentioned. We support multiple modes, but our preferred mode assumes that there has been a core set aside for operating system services, daemons, and that sort of a thing. It's common practice to set aside one to reduce any jitter that the OS could induce in the application, so the application stays off of that core that's been given over to the OS. GEOPM is just one more thing running in that reserved core in this scenario. Again, it isn't the only way you can run GEOPM. You can certainly run GEOPM on a core that the application is using as well. However, if you're doing anything heavyweight in the GEOPM plugin code, the application may notice an impact. So that's why our preferred mode has GEOPM running in a reserved core. These controllers all talk to each other across nodes. We do that currently in band on the network fabric and use MPI for that. Our benchmarks show that use of bandwidth is extremely low, almost imperceptible to the application. But if it ever becomes a concern, we encapsulated much of the communication code so that it's easy to target something else, like an out-of-band network. We haven't implemented that, but it's set up to be easy to do that. Any questions on the hierarchical architecture of GEOPM before I move on? Okay. Here's a quick look at how GEOPM integrates into the rest of the HPC stack, or a stack that we imagine there being for power management in the long term. In the long term, we imagine resource managers adding a layer of power awareness. In particular, we imagine them adding a component that we'll call, for purposes of discussion, a system power manager, or SPM for short. The SPM and GEOPM will work together for full system power management and optimization, and they'll talk to each other in one of two ways. We provide an API with GEOPM called the GEOPM to Resource Manager interface. That's one way they can talk dynamically. Another that's more static in nature is JSON config file interface. And based on the site policy, the SPM can decide how much power to allocate to different jobs or what constraints to set on the operation of each of the jobs in the system. Based on site policy, again, the SPM can decide what agent optimization plugin GEOPM will use for a given job. They can decide whether GEOPM should be trying to maximize performance within a power bound, or forgetting about power bounds, should it be optimizing for energy efficiency at whatever power that implies. The SPM can select that. And then we'll have one instance of GEOPM running with each job, enforcing that power budget or the other constraints given to it by the SPM. And while doing that, carry out whatever optimization the SPM selected. We're exploring models where GEOPM runs with all jobs. And in the near term, we've set up GEOPM so that it can run standalone and opt-in. That's because power-aware resource managers are still under development. So in the near term, we'll have job level management only. You can certainly have GEOPM running with every job in the system if you want, and you opt into that. But what's missing is the SPM and no coordination across GEOPM instances across jobs. So there's not any coordination of GEOPM optimizations across jobs if you use it today.
Hey, this is Tyler at Argonne.
Was there a question?
Yeah, I have a question. This is Ty at Argonne.
Okay, go ahead.
Do you envision, so let's say a user brings their application and they know that they should expect, a runtime of X at full power. Will GEOPM handle figuring out what that delta of X is and work with the resource manager to increase or decrease requested wall time for the user based on the power budget being requested?
That's a good question. It's a capability we could build into GEOPM. I mean, after all, we designed it to be pretty extensible. Forecasting of runtimes isn't something that we do directly yet. We do some forecasting of the time it takes to complete iterations in an application. You may actually be able to extrapolate from there if you have an iterative application. So we've actually been doing some development right now on the interface between the resource manager and GEOPM, trying to figure out what information they need to exchange, and that is one thing that we could look at adding.
Okay, thank you.
Any others before I continue? Okay, in the near term, GEOPM is opt-in. A user will request GEOPM and select which agent optimization plugin you want to run while they're queuing up their job. We provide wrappers that enable them to do that. We wrap popular job queue tools like Craze, AppRun, and Slurm's SRun. You use the options that those normally expect, but you can add geo-specific options at the end, which our wrappers will intercept and pass on to GEOPM. You can also configure how our GEOPM agents behave with a JSON config file. You can, for example, tell our agents how much power budget they have for the job, etc.
We have one more question. Is
Sure.
GEOPM implemented on the system admin level or the user level?
Well, right now, the user opts into it, and it, in the future, we actually may make it to where the user doesn't have the ability to opt in or opt out, and it's a site policy whether or not GEOPM is running. there's not much changes required to our code base to support both of those scenarios. Did I address the question you were really trying to ask? Okay, I'll assume so.
Alfred says he's not sure. He's not sure yet. So we can follow up at the end.
One other thing that may address that question, or another one that's in people's minds, is what privilege level GEOPM runs at. It is a user space runtime. It is not part of the kernel. By design, we don't want it to be running in kernel mode. It relies on drivers like the MSR safe driver to access controls and monitors in the hardware in a safe and high performance way. But it's a user space runtime. Launches with and runs alongside your application. Okay, on this slide I've got a laundry list of use cases we imagine for GEOPM. I don't have time to run through all these in detail. And we've been talking mostly about the first one, which is leveraging built-in optimization capabilities in GEOPM to optimize workload, performance, or energy. But I want to highlight a couple of others that are simpler in my mind, that don't involve optimization per se, but involve GEOPM's monitoring and reporting capabilities. This is something that may be of interest to developers. You can use GEOPM's reporting capabilities to characterize runtime and energy and other statistics of your application or even individual phases within it. With GEOPM's APIs, you can mark up a region of interest in your application and study the cumulative runtime, energy, or other statistics for that region of code. That can be really helpful if you're looking to tune your application for better energy efficiency or performance in future power constrained systems. And so, you can leverage GEOPM's reporting capabilities for that, independent of optimization. Admins and researchers may also be interested in using GEOPM for monitoring. You can monitor job level aggregated statistics or even system statistics if we glue GEOPM into a broader system monitoring framework. And all you need for that is GEOPM's reporting and tracing capabilities. We do actually support some tracing, so every control interval in GEOPM, you can get a dump of the signals that is collected from the hardware or from instrumentation of the software. You can also get a sense of what settings it applied to the hardware control knobs and leverage that stuff for monitoring purposes. The control interval of GEOPM is configurable by default. I think we have it going to 5 milliseconds currently, so you may not want data at that volume, that rate. We'll look into aggregating it through downsampling or something to that effect. It's also, tracing is not on by default, but you can turn it on. I also alluded to researchers, vendors, or integrators wanting to extend GEOPM to new optimization strategies or port GEOPM to new hardware architectures. So that's covered in the table of use cases here too. But those are the main ones that I wanted to highlight. Any questions on use cases before I move into the deployments that we're working on for GEOPM?
Yes, we have a question. The GEOPM control process can be owned by the user or the resource manager, and all the communication between the control process and the application is done over shared memory. Oh, I'm sorry, that's not a question, it's a comment.
Actually, our preferred method of, GEOPM supports several methods of launch. Our preferred method has it being a separate MPI application that runs on the same compute nodes as the primary application. And it will talk to the application, that is true, it'll talk to the application through inter-process shared memory, and GEOPM processes on different compute nodes talk to each other through the in-band network fabric over MPI presently. So that's one way, our preferred way of launching GEOPM resource managers like Slurm allow you to have multiple MPI applications running on the same compute nodes, but it isn't possible in every environment. So we also support cases where GEOPM can run as part of the application, and we have some launch wrappers that, behind the scenes use PMPI instrumentation to get GEOPM injected into the application. We kind of spawn an extra rank and leverage the same communicator that the application has for doing MPI communication across GEOPM control processes. In the future, we may even make GEOPM launch be completely controlled by the resource manager, but presently the user opts into it and can specify the launch method that they want. Any more questions on that before I move on to deployments? Okay. GEOPM is part of Intel's Exoscale solution. It's a key pillar for reaching the aggressive performance and power targets of Exoscale. And it'll be deployed in A21, assuming Intel and Argonne go forward with that. They're working on a contract to build a system called A21, which will be the first US Exoscale system. If we do broader Exoscale systems as intended, GEOPM will be a key pillar of those Exoscale systems as well. But it isn't all about Exoscale. Like I was saying earlier, we are targeting nearer term systems too, because there's a lot of benefit that GEOPM can provide on them. One is the Theta system. We are working with Argonne to get GEOPM onto the Theta system this year. The cool thing about that is it'll provide a vehicle for testing GEOPM at scale and in production settings, and will also be a nice platform for ALCF folks to do research in the power and energy optimization leveraging GEOPM. We're also expecting to put GEOPM into production on a system in Europe at LRZ, a system called SuperMUC NG, working on that this year and early next year. And one of the really neat things about that system is that there is a strong emphasis on minimizing energy consumption, because electricity pricing in Europe is extremely bad compared to the prices that we enjoy here in America. Even you can see how much emphasis there is on it even in the way that the contracts are structured. There's a large portion of the contract that is set aside for the electricity that the system is going to consume over its lifetime. Electricity is usually something that's like handled independently of the contract. Beyond those systems, we're also working on broader deployments through OpenHPC. Many of you know what OpenHPC is all about. We've got GEOPM accepted into OpenHPC and are expecting GEOPM to be included in the next big OpenHPC release that should happen right before SC18. So that'll be cool. We'll get GEOPM on additional systems through OpenHPC and broaden the community of users and developers. Any question on that stuff before I move on to experimental data? All right. I do want to share with you some of the... okay, sure.
Zingfu asks, how much information does GEOPM need from PMPI profiling? Does GEOPM support Python code?
We get a very minimal amount of information from PMPI because we want the instrumentation to be lightweight. We want to know things like how long MPI calls are taking, how much cumulative time is spent in MPI calls. In the future, we may even kind of capture a lightweight trace of a sequence of MPI calls that have happened and use that to automatically detect where global synchronization collectives are, things like that. Pretty lightweight though. GEOPM provides C interfaces. You can call into GEOPM from many different programming languages as a result, pretty much anything that supports C bindings. The plugins for GEOPM, if that's what the question was directed at, those are those currently have to be in C, although we could look at supporting other stuff. All right, if there aren't any other questions on that, I'll move on to data from our experiments with GEOPM to quantify the performance and energy efficiency benefits that it can bring. The first thing I want to talk about is experiments we've done with one of the built-in plugins for GEOPM, which we call the power balancer. We developed this to demonstrate, well, a couple of things. One, demonstrate the benefits of application-aware optimization techniques, the added performance and energy efficiency you could get from application awareness. We also wanted to demonstrate the global, hierarchical nature of GEOPM with this algorithm. So here's what it does. This is meant for iterative bulk synchronous MPI jobs and meant to be used in power cap scenarios where the system power is constrained like we expect it to be in exascale systems. And what this power balancer plugin does is identify if there are any nodes that become a critical path in the application and limit the time to solution of the application. And if there are such critical path nodes, the plugin figures out how to reallocate power among the compute nodes to give more to the critical path nodes at the expense of taking some away from the off critical path nodes for an overall improvement in time to solution. And where that improvement comes from is that we are avoiding wait time at global synchronization points. I'll give a little bit more background on why that is in the next slide.
So I think you might have just answered the next question, but I'll put it out. What is the user's incentive to optimize power consumption if it does not affect how the code runs on the user's end?
That is a good question. In current systems, we're not bumping up against system power constraints in all systems around the world. There are some sites where power is constrained. Japan, for example, there isn't enough power to fire up their systems and run at full performance because that would mean they couldn't light up all the classrooms that are sharing that power. There are also some centers that want to use renewables where the amount of power that's available is variable throughout the day or season. And in those cases, trying to cap power makes a lot of sense. In the current systems in the United States, the main benefit of GEOPM is, well, there are several really. One is getting ready for the reality that power is going to be capped in future systems. And the other is that in the nearer term, we can shave some millions of dollars off of the electricity bill by maintaining current levels of performance, but producing those levels of performance at a lower power. We'll talk about another plugin in a moment that tries to do just that, try to reduce the electricity bill. So that's incentive for the site. End users typically haven't paid much attention to the power consumption of their workloads, and maybe they don't have any incentive presently to run GEOPM, but that is going to change. You're going to see sites enforcing policies that require users to run with better energy efficiency, and maybe the incentive that they'll give to users is shorter wait times in the job queues, or maybe they'll change the way you're billed for jobs so that the electricity consumption of them is one of the factors that determines how much you're billed. That stuff's being worked out. I'll also say that we have some research underway that leverages the GEOPM framework for different kinds of optimizations that are more performance oriented. So forget about power capping, forget about energy efficiency, but rather we're trying to tune hardware control knobs to produce better performance. And that's something that's in the research stages right now, but something that is a lot more directly relevant to users on current systems who care about performance. So let me get back to this power balancer plugin. Tell you a little bit about how it speeds up iterative bulk synchronous MPI jobs. Where do we get our feedback? Again, this is feedback guided optimization. We get that feedback from programmer provided annotation of the application's outer loop. We provide an API with GEOPM that allows the programmer to tell us where one of these outer, where one of these global synchronization operations is going to occur. And then our Power Balancer plugin measures the time between executions of an API call to measure how much time each node is taking to complete that loop. Plugin then compares the loop times across nodes to identify which nodes are going to be on the critical path and even get a sense of how far off the different nodes are, so we know how much power correction is needed. And then the actual reallocation of power, the way we do that is by configuring each node's power cap. On the Intel systems that we did these experiments on, we have a feature called running average power limiting in Intel processors that allows you to set a power cap for the processors, and we're reconfiguring that as we go along to set new power allocations. I promised you some background on why it is that you may actually have some nodes becoming a critical path. And the short answer is manufacturing variation. In these iterative bulk synchronous programs, the nodes frequently wait at a global synchronization point. They exchange some data with the other nodes. Once they get there, they wait until all nodes have reached that point before they begin the next iteration. Obviously, if some nodes are arriving late, everybody's waiting, we waste power, and we're losing some potential performance. So how does this situation arise where some nodes are arriving late? Even if all of the work is evenly divided among the nodes, and it isn't always, but even in the cases where it is, some nodes can fall behind due to performance differences across the nodes. They may be given the same amount of work, but take a different amount of time to complete it. So where do those performance differences come from? Turns out that when you're doing power capping, when the power of a job is limited, the nodes can achieve different frequencies. When you put a power cap on the processors, they can achieve a different frequency at a given power cap. And the reason for that is manufacturing variation. They have different power efficiency. It requires a different voltage to operate correctly at a given frequency. And so when you turn that around and you apply a power cap, you can get to a different frequency before you've used up the power. Interestingly, this is true and a problem even if you take processors from the same product SKU. There's some variation even within an SKU because we don't have an infinite number of SKUs. We try to, bucket similar processors into the same SKU, but you can still observe variation in frequencies that they achieve under power caps in several hundred megahertz. Pretty substantial. All right, so we evaluated this Power Balancer plugin on a Knights Landing cluster, looked at Coral procurement benchmarks plus a molecular dynamics app from XModX and Fourier transform app from the NAS Parallel Benchmark Suite. I've got the experimental setup listed in this table. The salient points are that we ran on 12 Knights Landing nodes, all from the same SKU. We had turbo enabled in these experiments. The sticker frequency was 1.3 gigahertz. These processors have a thermal design power of 230 watts. We ran with GEOPM on a core reserved for the OS, application staying off of that core. And yeah, those are the salient points in the experimental setup. What we looked at was time to solution in two scenarios. One in which we are using the Power Balancer plugin with GEOPM and another where we have taken a job power cap and uniformly divided it and applied that uniform power cap across all of the compute nodes in a job statically for the lifetime of the application. When we're running with the power balancer, on the other hand, we are dynamically adjusting the power allocated to each compute node and deliberately allocating the power non-uniformly. We want to study a range of assumptions about how much the job is power capped, so we swept over different power caps and focused on what we consider to be the region of interest. We set the low end of the power caps to avoid unrealistic scenarios where the processors are kind of panicking to achieve that power cap. We don't want that. We want them to be doing efficient power reduction techniques like DVFS rather than inefficient ones like clock throttling. And at the high end, we chose the high end of the power caps to be the unconstrained power consumption of the workload, meaning that if you were to set the power cap any higher, it's not possible for the workload to use any more power than that because all of the processors are already running at full frequency. The main result of these studies is that we were able to demonstrate up to 30% improvement in time to solution at the low caps for Mini-FE and AMG from the Coral benchmark suites and CoMD from XModX. For the others, we were able to demonstrate 9 to 23% performance improvements, time to solution improvements. Pretty substantial considering that we're doing this with software and not assuming any special hardware support. I've got 3 of the charts on this page. These are showing runtime, so lower is better. And we're comparing, again, the power balancer plugin in GEOPM versus a static uniform division of power and sweeping over different power limits, where the power limits are expressed in averages for each node. First 3 charts are on this slide. Let me flash these really quick. They wouldn't fit on the slide. Other 4 workloads that we looked at are on this slide. As a general trend, what you see is that the amount of benefit that the power balancer plugin can provide is highest when you're capping job power more, when the job is more power constrained. As you would expect, when you're not constraining job power, there isn't much opportunity to raise the frequency. There isn't any opportunity to raise the frequency of critical path nodes, and so the power balancing technique can't provide any benefit there. The reason that the benefit is higher when you're more constrained is that you expose more and more manufacturing variation the more capped the processor power is. So it's more and more important to be reallocating power among compute nodes to correct that. Any questions on this before I move on to another plugin that we studied? Okay. Let me talk next about an additional plugin that we provide out of the box with GEOPM, which we call the energy efficient plugin. It, like the name suggests, optimizes for energy efficiency at whatever power consumption that may imply. It doesn't, try to maximize performance within a power bound, but rather tries to find the hardware control knob settings that allow the workload to run with better energy efficiency, subject to a constraint that we don't degrade performance by more than some percentage. This is work we're doing in collaboration with LRZ, Chineka, and Unibo. And what the plugin does is try to detect different computational phases inside of each node, in particular looking for phases that are memory limited or MPI communication limited, and then reduce the frequency that processor cores are running at during those phases, because you're able to do that without impacting the runtime of these phases very much. Because they're memory limited or MPI communication limited, if you were to run the processors at full frequency, it wouldn't improve runtime. You're just generating memory or communication operations faster than the memory system or communication system can satisfy them. So instead, we're trying to reduce the frequency and save power in the compute portion of the hardware. I won't go through all the studies that we did here in the interest of time, but I'm particularly proud of some of the initial results we got with Gadget, which is a cosmology simulation code that runs on many machine cycles at LRZ. Our early data suggests that it's possible to get in excess of 17% energy improvements with only modest 7% impact to application performance. My collaborators at Unibo tell me that they've been able to get better energy improvements, a comparable performance impact for the Quantum Espresso benchmark suite. They've been seeing something like 30% improvements. Any question on this? Oh, I should have mentioned that these studies were done on a Xeon system, in particular a Broadwell system in production at Livermore called Quartz. Any questions on this stuff?
Where's the baseline?
Yes, there's a question on the chat. What is the baseline for normalizing the runtime?
We compared against, let me think, let me try to remember actually. I don't want to tell you something wrong. Okay, in the left column, I think what we've compared against is running the application at sticker frequency, or at most a couple hundred megahertz below that. And instead of running at that fixed frequency, we find the energy optimal, we find the optimal frequency from the perspective of energy consumption, subject to the constraint that we don't degrade time to solution by more than some configurable percentage. In the right column, we are doing optimization of the frequency on a per phase basis. So we find a different frequency for each application phase in the application. And there we're comparing against, again, I think running at either sticker frequency or no more than a couple hundred megahertz below it. We think there's more benefit to be had by adapting the frequency on a per phase basis rather than finding it best fit across the whole application. And that's because, like I mentioned earlier, different computational phases in an application can have wildly different runtime versus frequency scaling. And if you apply a best fit across all of them, you're really kind of doing something suboptimal for each of them. So this is very promising early work that we're doing in collaboration with LRZ, Chineka, and Unibo. And we're working toward, well, A, completing that, and B, deploying it on SuperMUC and G, as well as the Marconi system at Chineka. That one's a Knight's Landing system, and the LRZ system. Well, actually, Marconi's heterogeneous. Knight's Landing is part of it, and LRZ's system, the SuperMUC and G system, is a Skylake system. All right, quick time check. How much time do I have left?
Well, we're coming up on 12, but we can go a few minutes over.
All right, then I'll go through this very quickly and try not to go over much. Just wanted to give you a sense of what we're working on now and in the near future. One of the things we're working on very feverishly at the moment is prepping GEOPM for general availability to the ALCF community on IOTA and Theta. Another is that we're prepping for GEOPM to be included in the upcoming Open HPC release, coinciding with SC18. And another is that we are prepping for the 1.0 release of GEOPM, which we're expecting at the end of this year. We're also working on a number of extensions to GEOPM, along with our collaborators. That includes the stuff I just mentioned on the previous slide, as well as a port of GEOPM to new architectures, like the Open Power plus NVLink microarchitecture. We're also working on extensions to tuning parameters in software, like tuning the thread concurrency level, like I mentioned earlier. And another major thrust for us in the near future is going to be integrating GEOPM with other components of the HPC power stack for the purpose of scalable monitoring and system level management, system level power capping, power over scheduling, system power forecasting, and things of that ilk. Longer term, we've also been doing work in the co-design space, trying to not stop with software, but enhance the hardware and firmware in Intel processors so that runtimes like GEOPM and GEOPM can get even better results, better performance benefits or energy savings. Been looking at improvements in the processor, controls and monitors, memory controls and monitors, and things of that ilk. So I'll close with some takeaways and a call to action to join the growing community of GEOPM users and developers. I hope I've convinced you that there are pretty substantial performance and energy benefits that you can obtain with application-aware power management algorithms that are able to see across nodes and understand things like load imbalance and computational phases. We certainly demonstrated some of those in the data I shared today and in the ISC paper we've done on GEOPM. But it doesn't stop there. You can explore your own algorithms, leveraging the plugin infrastructure in GEOPM. You can port GEOPM too to target architectures beyond the Intel systems that we've studied and beyond the Open Power and NVLink port that's in progress. I mentioned too that GEOPM is coming soon to IOTA and Theta, as well as other production systems. So look forward to an announcement about that. We'll give a specific date pretty soon. We're kind of working that out. Next, I'd say give GEOPM a try. We'd love to get your feedback. We need that feedback to polish our code for the 1.0 release, which is anticipated at the end of this year. So we'd very much appreciate your feedback. And last, please join the community of GEOPM users and developers. We have a Slack channel where you can get support from us. You can also send me email with questions or even feedback. We are in the process of setting up a tutorial on GEOPM for this audience in the ALCF community, and in the process of making GEOPM available on IOTA and Theta, as mentioned. If you want further information on GEOPM, take a look at our ISC 17 paper. I provided a link there below. And of course, you can go and look at our GEOPM project page as well. There's the link on GitHub. There we have tutorials for how to use GEOPM. Of course, there's the source code. We have thorough user and developer documentation, and also instructions for how to contribute to the project. So with that, I'll stop with the acknowledgements and acknowledge all the folks that are contributing to this, both on the software and hardware/firmware side, and take any questions that you got.
So, Jonathan, you just talked about the potential tutorial. So I just wanted to take a little straw poll of the attendees here. For folks, how many of you attending today would be interested in attending a webinar tutorial sometime soon to have a deeper dive into using and getting started with GEOPM?
We'll cover stuff like how to run GEOPM, how to mark up applications, and if time allows, we'll even talk about how to extend GEOPM, develop new optimization plugins.
Okay, it looks like we have 4 people interested so far. Okay, and we also had another, okay, so thank you, and we'll be sure to let you know what we set up. It would be using Theta, and we have to check the status and make sure that we have any site-specific documentation set up. We also had a question on the chat. How does GEOPM deal with I/O-intensive applications?
I/O intensive as in they're accessing the file system a lot? I assume that's what they mean. We haven't looked at that very much, to be honest. It's an interesting area of research, though. There aren't very many control knobs, at least not that I'm aware of, for controlling power in the file system. So it isn't exactly obvious to me what you would do if you were trying to optimize for an I/O intensive workload. But I'll say this, the GEOPM framework is highly extensible. If there are knobs or even monitors of the the I/O in the system that it would make sense to support, it isn't very difficult to add support for those in GEOPM and tinker around with optimization algorithms that are aware of I/O.
So I don't know if the person asking was trying to take into account power used in the I/O subsystem, but if that's not the case, I suppose if the application is engaged with I/O and primarily waiting on the I/O to complete, then turning the power down would be fine because it's not actually in heavy compute at that point.
You're right, it's a good point. There should be lots of opportunity for reducing processor core frequencies and saving energy without much impact to performance.